I am Eliza Siefert. I'm the critical materials water researcher here at the West Virginia Water Research Institute. And today I'll be talking about rare earth element and critical material recycling from acid mine drainage, or as I like to call it, recycling. Okay, so just a little bit about WRI. So the West Virginia Water Research Institute is supported under the Federal Clean Water Act, and we've been serving the state of West Virginia since 1967. We're at Morgantown, West Virginia, and housed in WVU, and we collaborate with other WVU colleges, other higher education institutes, private consultants, and industry professionals to focus on economic development, education, outreach, and research to solve water quality issues across the state. Our activities are overseen by the West Virginia Advisory Academy for Water Research, which includes federal and state agencies, academia, and industry professionals. So the work that we do cannot be done in a vacuum. So there are numerous other entities involved with the research we conduct, including the Department of Energy, the West Virginia Department of Environmental Protection, Virginia Tech, Montana Bureaus of Mines and Geology, Solmax Geosynthetics, and Montana Resources. So first, just a little bit about acid mine drainage. So acid mine drainage forms when pyrite-rich geology is exposed to air and water. So this can occur often during mining practices, but can also occur during any large land movement activities such as highway construction. So this pyrite or fool's gold gets oxidized and forms sulfuric acid, which is a very strong acid. And so then this sulfuric acid is able to leach heavy metals and other elements from the other rocks nearby. And so when the pH gets right and it enters the stream, we can end up with the lovely orange-yellow creek as we see on this right-hand image. So acid mine drainage is a worldwide issue and treatment can be very costly. So for example, within the state of West Virginia alone, there are 2,500 stream miles impacted by acid mine drainage. So now on to rare earth elements. So there are 17 elements considered rare earth elements. And when we think of the periodic table, it's the block that sits underneath the table, but just that first row down there. And so these are used in catalysts, cars, cell phones, technology. Currently, there's a very large demand for rare earth elements, but not a large supply. And they're called rare earth elements not because they are uncommon. In fact, they're actually quite abundant in our Earth's crust, but they are found in such low concentrations. So currently, most of the rare earth elements are mined in China, and the United States does not have their own supply chain of rare earth elements without relying on foreign entities. So in 2016, the West Virginia Water Research Institute found that rare earth elements exist in raw coal acid mine drainage across 140 separate sampling sites. We also found two critical materials, namely cobalt and nickel, were found to be in a 1-to-1 ratio with these rare earth elements in the acid mine drainage. So just a quick little timeline. In 2015, the Department of Energy released a funding opportunity to find rare earth elements in unconventional sources. And at the Water Research Institute, we found them in coal acid mine drainage. So with that, in 2017, we developed a two-stage acid mine drainage treatment. And in turn, we treat acid mine drainage to discharge compliance, as well as generating a rare earth element feedstock that we can use for further processing and purification. So from 2018 to 2020, we took that rare earth element feedstock and we did a lot of benchtop pilot system designs and testings to be able to purify that to rare earth element products. And then we really used the COVID time to go full scale. So currently we have a rare earth element recovery plant in Mount Storm, West Virginia. This is in conjunction with the West Virginia Department of Environmental Protection. One half of the building is an acid mine drainage treatment plant that treats up to 50 gallons per minute of acid mine drainage. And the other half, we take that pre-concentrate that's formed when we treat the acid mine drainage and we further process it to make the mixed rare earth oxide products. So, as I said, we developed this two-step acid mine drainage treatment system that treats water to compliance as well as generate us with a rare earth element pre-concentrate. So just quickly walking through the schematic, the acid mine drainage enters on the left and gets dosed with lime to a set pH. And then the solids that settle out are rejects and go for whatever disposal methods currently permitted at that site. The effluent water from that first pH cut goes on to another clarifier and more limes added to raise it again. And then that water, once the solids have separated, is treated water and is safe to discharge, while that solid that comes out of that clarifier is our pre-concentrate that we use for further rare earth element processing. So through this, we will generate roughly half the amount of sludge reject as a conventional acid mine drainage treatment, because the other half is this rare earth element pre-concentrate that we use for further processing. And so I will say that every site is different. So not all sites are going to justify processing through exactly this ways, but there are different steps and circuits we can add to accommodate each site's requirements. So regardless, this rare earth element pre-concentrate can then be processed into a mixed rare earth oxide, and then it'll go on to elemental separation. So the hydraulic pre-concentrate, or the rare earth element pre-concentrate, we can either process it as a slurry, as you see in the beaker in the lower photo, or as a solid. So we can pump it to geotubes to allow for passive dewatering. There's an example of a geotube on the far right. So we worked with Solmax Geosynthetics to develop an optimal geosynthetic for rare earth element capture. So essentially, we would just pump this pre-concentrate into the geotubes, allow it to dewater, and this just makes it easier for long-term storage and transport. So when it's dewatered, it looks roughly like the middle image, honestly, just kind of like dirt. So either way, whether it's a solid or a slurry, the pre-concentrate will undergo acid leaching and solvent extraction. Essentially, each step of the process, we are getting the rare earth elements more and more concentrated in smaller and smaller volumes, until eventually we have the solvent that's super enriched in rare earth elements, and then we acid strip it to remove the rare earths. And then those rare earths can get purified into a light and a heavy rare earth oxide product. So, as I said, in Mount Storm, West Virginia, we are currently producing a mixed rare earth oxide. So this is an automated system capable of being remotely monitored, and light and heavy rare earth oxides are currently being produced at greater than 90% purity. So this is treating a 500 gallon per minute acid mine drainage inflow rate, and with that, we have the ability to produce roughly 1.7 metric tons of mixed rare earth oxide a year at this site. And so the image below is just an example of what the light and heavy rare earth oxides can look like through the process. So the final report for the project where we developed the pilot plant at Mount Storm, West Virginia is publicly available. So I put up this lovely QR code to allow you guys to easily access it if you're interested in reading more. And so with this, we are continuing to restore acid mine drainage impacted watersheds while recovering critical materials and rare earth elements, with the goal to utilize this money to cover plant operation and maintenance. So this map here in the bottom right corner is a map of the unemployment rates in the abandoned mine lands within West Virginia. So the counties where the unemployment rate is greater than 5% is highlighted in red, and all of the abandoned mine land sites within the state are the gold dots. So as you can see, there's a real opportunity here to develop additional jobs in depressed regions of Appalachia. So our rare earth element program goals at the Water Research Institute are first and foremost to incentivize acid mine drainage treatment by encouraging more operators and landowners to treat acid mine drainage on their property, and in turn restore more watersheds and streams. This would provide cost savings to reduce operation and maintenance costs for acid mine drainage treatment and create additional jobs for economies that are currently dependent on coal. And finally, we are looking to develop an independent rare earth element supply chain within the United States. So I'm going to jump into some FAQs we frequently get, but if you have any more questions, like I said, there'll be more time for those at the end. So first things first, who gets the benefit of rare earth element recovery from acid mine drainage? Well, for the state of West Virginia, whoever treats the acid mine drainage gets the money. So in 2022, the West Virginia state legislature enacted House Bill 4003, which pretty much states that the entity who treats the acid mine drainage gets the economic benefit from any byproducts. So, for example, if the West Virginia Department of Environmental Protection were to treat AMD and generate rare earth element products, any money generated could go towards covering operation and maintenance for their treatment systems. So this is legislation that West Virginia led on, and there is an opportunity for states to do similar. Very preliminary studies have indicated that there are interest in other states for similar legislation, though it may not be as black and white as the legislation has currently been written in West Virginia. Hey, another one. So, is rare earth element recovery environmentally beneficial? Long story short, yes. So our goal is clean rivers and streams. We genuinely would not try anything or do anything if we felt it provided more harm than good to the environment. So our entire process is environmentally benign. Nothing will exit our treatment system. Again, our only discharge is treated water to NPDES compliance. So we have numerous conductivity and pH controls and check valves throughout the entire system. So when one of these controls senses something is wrong, all the check valves will close and the system shuts off. So in turn, if something's off, nothing's going to process and nothing's going to leave the system. And then additionally, all of the extractants we use for the process are recycled, which limits the volume we have to have on site. The upstream process where we produce the rare earth element pre-concentrate is the same as conventional acid mine drainage treatment. It uses lime, which is used commonly in both passive and active acid mine drainage treatment systems. The downstream process where we recover the rare earth elements from the pre-concentrate does not generate any hazardous byproducts. So we have done toxic characteristic leaching procedure or TCLP testing on the products at intermediaries. And so this essentially tests for different hazardous materials, and they have all come back at acceptable levels. With every sample we analyze for thorium and uranium. And again, they've always come back at acceptable levels. And finally, we've had products on our intermediaries tested for gamma, beta, and alpha radiation from the WVU Radiation's Safety Division. And they told us it's not a concern. The amount of radiation coming off of our materials was the same of that as a banana. So overall, fairly safe. And then finally, our only offsite discharge is water that's treated to NPDES compliance. Okay, so will rare earth element recovery promote additional mining? Long story short, no. So rare earth elements can only be recovered from acid mine drainage during treatment. No rare earth elements can be recovered from traditional mining methods effectively, especially in the eastern portion of the United States. So rare earth element recovery offsets operation and maintenance costs, but the revenue generated does not justify additional mining just to create more acid mine drainage to extract rare earth elements from. Rare earth elements may pay for part of, but not much, if any, over any treatment cost. So for example, at the Mount Storm site, the projected revenue of the rare earths just barely offsets the cost of the operation and maintenance for that site. And the projections we have done for other facilities has been the same. So our goal is to incentivize acid mine drainage treatment at abandoned mine lands through cost savings. So with abandoned mine lands in the state of West Virginia, any money generated would go back to the West Virginia Department of Environmental Protection, which could then again aid in operation and maintenance costs. So our goal again is to incentivize treatment so we have clean rivers and streams and to create a domestic supply chain. So we are ensuring we're getting rare earth elements in less extractive methods than we currently are obtaining them from. Okay, final little FAQ. So what are polymers and why do we use them? So overall, polymers are natural or synthetic macromolecules that increase the size of flocculated particles. The easiest way to think about this is you add floc into water treatment and it essentially acts like a glue for different particles to bind to. Essentially, this glue makes them heavier and allows them to sink, which makes them easier to recover and makes water treatment overall cheaper. So through this, because they're larger in size and heavier, we minimize the risk of contaminant solids from passing through any treatment systems. And it helps to reduce processing costs because it already separates these particles from the water for us. So it increases the rate of sludge settling and allows more water to be treated per given time. And polymers are used commonly in both acid mine drainage treatment processes, and we also utilize them at points within the rare earth recovery process as well. So looking forward, the Water Research Institute is identifying additional acid mine drainage sources for treatment and potential rare earth element recovery. We are currently aiding the West Virginia DEP in identifying abandoned mine land sites to restore through bipartisan infrastructure law funding. And so some of these sites may work for watershed scale restoration, which Nate can provide more information on in his presentation coming up. And so with this, some but not all of these sites may also include a rare earth element extraction process with it. And so all in all, we are looking to develop this independent United States supply chain of rare earth elements to make sure we are obtaining these very necessary minerals from better means than we currently are. So all of the information I went over, we pretty much have available on our website in these lovely AMD WVWRI fact sheets. So there's a QR code up in the top right-hand corner, and you can access all of those through the site. And there's a lot more information about what the Water Research Institute does and our rare earth element processes. But with that, thank you so much for listening, and my contact information is up there if you would like to contact me separately, or feel free to ask questions once everyone's done presenting. Thank you.
All right, if no one has any immediate questions for Eliza, I will proceed. Well, good morning, everybody. Thank you for joining us this morning on this day after New Year's Day. Hope everyone had a great holiday season and start to the new year. My name is David Hoffman, and I am the Critical Materials Program Manager here at the West Virginia Water Research Institute. So Eliza and Nate and myself all work directly together, as well as other individuals from the Water Research Institute to kind of make everything happen. So my specialty is in the critical materials extraction area, downstream of the AMD treatment, but I work in conjunction with the other groups to kind of make all that go together in one path. So today I'm going to be presenting kind of really what I call the story of the rare earth program here at WRI. Talking about the recovery of rare earth elements from acid mine drainage feedstocks and kind of how we've developed this over the past several years since 2016. Some of the material is a little redundant to Eliza's presentation, so there might be some things that I don't touch on as much that are in the slides because Eliza has kind of given you guys a lot of the background. So Eliza did highlight our partners earlier. Here at West Virginia University, Dr. Paul Zimkevich is the director and did come up with this program. I am currently the manager and director of the critical materials program. Dr. John Caranta really did the early development of the geosynthetic capture, and that has since transitioned to Dr. Nathan DePriest, who's going to be presenting later, and he is the lead of the engineering department here at WRI and really heads up the geosynthetic capture. From Virginia Tech, Dr. Aaron Noble has led their development and partnership with us on these projects. He's the department head of mining and minerals engineering. We also work a great deal with a group called L3 Engineering. Dr. Tommy La Rochelle is the lead for the projects on that, and he's a process development engineer. And as Eliza said, we are also very closely partnered with West Virginia DEP, Rockwell Automation, and Solmax, formerly Tenkati. So why are we here? Why are we talking about this? Why is this so important to, do this presentation on and kind of this whole seminar series? So the United States does rely upon several rare earth elements and critical minerals for the use and manufacturing of national defense related items. As of December 2024, China has officially banned the sale of gallium, germanium, and antimony to the United States. This is a really big development that we really don't know the effects of quite yet because it's so new. But in 2023, China put a restriction on gallium and germanium, which caused a 63% price increase in germanium and a 34% price increase in gallium. And those are very two specific elements, and the reason they're important is because they are used highly in defense, but also gallium is really a driver in the computer chip manufacturing and all the artificial intelligence equipment that is kind of being developed here very rapidly. It's very key in that. So losing the ability to procure that material is going to be a very big issue for the United States. Now, those are really considered critical minerals. So, and we're really after rare earth elements. So the gallium, germanium, and we mentioned antimony is kind of a new development as part of this AMD treatment. It is not found really in the AMD in West Virginia, but is really found in what we called hard rock AMD, which is primarily on the West Coast. We also have seen it in some other acid mine drainage on the East Coast as well. So, different sources might have different amounts of some of these critical minerals, whereas rare earths we're really finding a consistent amount in AMD and what we call ARD, acid rock drainage in the West. With that being said, the ban of gallium, germanium, and antimony, it is kind of theorized that there is going to be a ban on the other rare earth elements in the near future. So that's kind of a preparation for that as well to secure that supply chain domestically. The other thing that the United States is particularly up against is what's called the DFARS Act. This act is put in place by the Department of Defense and their federal acquisition regulations. Basically, in December of 2026, that will require any rare earth elements or critical minerals to be sourced outside of China for defense purposes. China, as Eliza said, is the largest supplier of rare earth elements and critical minerals. There are some sources in Australia and Japan, but not enough to meet the supply chain needs. So this is also a very large driver for the rush of the development of rare earth element capture from any feedstock really, but where we're looking at is acid mine drainage. So why is acid mine drainage really significant in this challenge? So what we found in acid mine drainage that's consistent across both acid mine drainage in Appalachian coal, acid rock drainage in the Western United States, as well as other AMD sources kind of to the south of us and to the west and east, is that the heavy rare earth elements are at a 45% distribution in the AMD. And why that's significant is most mine sources of rare earth elements are only seeing a 10% distribution of heavy rare earths. And especially the only rare earth mine in the United States, which is called Mountain Pass in California, has less than 10%. It's believed to be around 2% of heavy rare earth elements within their mining operations. So there's not a large source of what these heavy rare earth elements are. And the two that are really of large concern and needed in magnet manufacturing is terbium and dysprosium. And it is believed that if we were to make a 1 ton per day separation facility from acid mine drainage feedstock, that we would generate 7 to 8% of the world's terbium dysprosium supply. What is very interesting to this, by 2030, only 50% of the terbium and dysprosium demand will be able to be met by current suppliers of those materials to the market, which is primarily China. So the United States, once again, really can't even get its hands on, might not be able to get its hands on it by that date anyhow. But there is a significant deficiency in the manufacturing of that material that's going to be coming upon us very, very soon. So now going into our story of how this kind of all came to development. So as Eliza said, in 2017, we developed a 2-stage treatment model. The real glory of this is it is very similar to AMD treatment as it already sits, and really just requires 2 clarifiers with independent pH control. And then the other, large benefit of that is the ability to meet the water compliance criteria. So our A34 plant has not had any compliance issues by adding this rare earth capture stream in. And as Eliza said, by making 2 separate sludges, or one we call hydraulic pre-concentrate, we decrease that sludge disposal cost because we're essentially taking half the material and using it for further uses downstream. So from 2016 to 2017, we did do our first project where we really did a evaluation to find if rare earth elements and critical materials existed in economic quantities in acid mine drainage treatment and its concentrates. So we did originally look at just basic AMD treatment sludge. AMD treatment sludge does have rare earths in it. The large issue with that is the presence of iron. The presence of iron is really problematic for downstream recovery of rare earths. So that is why the 2-stage treatment process was developed. As we went through and developed that process, the pre-concentrate that we came up with through the process was evaluated to see if we could economically both extract those critical minerals back out and if there was enough to, per se, transport it or process it. So we did evaluate several methods of recovering the rare earths from that pre-concentrate, and optimally settled upon acid leaching for the recovery. And solvent extraction was first explored during this project for the selective extraction of rare earth elements. So from 2017 to 2019, we developed this small scale field demo. What we did here was we essentially built a 2-split treatment facility within a mobilized trailer and developed that 2-stage treatment process into a continuous model within this trailer. This was successfully deployed, and we were able to generate, I would say, probably at least 20 5-gallon buckets full of the hydraulic pre-concentrate that we then used for further extraction. Concurrently, we had a separate project in 2018 from 2019 where the acid leaching and solvent extraction circuit was developed. What was very important to this was to develop a economically efficient process that captured the rare earth from the pre-concentrate to make a pregnant liquor solution, which is basically your leachate with all the rare earths in it, and hopefully not a ton of what we call gang materials, but materials not of value that we do not want going through the process. Furthermore, once you get into a solution, you do a extraction with a solvent. So this process was developed for the PLS. The extractants are in this project were somewhat conventional, but because of the amount of different things in acid mine drainage and what goes through the process, that was where the challenge was to find how to extract the elements without extracting other things. In this project, we also developed an automated SX system that was successfully deployed in the High Bay Research Facility on WVU's Evansdale campus in the NRCCE building. The system was installed in the project and successfully ran, and we are actually revamping that circuit right now, and it should be running full time, hopefully within the next couple of weeks. This project successfully generated a 90% pure mixed rare earth oxide product using the developed acid leaching and solvent extraction circuit. So in 2020, we were awarded a project by the Department of Energy to basically put in a full-scale pilot facility at Site A34, which is a West Virginia DEP treatment plant. So we partnered with West Virginia DEP to essentially add on to their facility and add an additional clarifier to capture the pre-concentrate and then take and process all the way to mixed rare earth oxides. We did have COVID occur during this project, which ended up being a really benefit to the project because it extended it. We were able to utilize the space in the High Bay Research Center to both build a clarifier that mimicked these rectangular clarifiers. So I will note that the rectangular clarifiers, and you can see them on the right, were the first of its kind that DEP installed. There was a lot of concerns about gathering that pre-concentrate and getting it to our process. I will say that these clarifiers have worked extremely well, and DEP has since put in, I believe, 3 other facilities. It might only be 2, but I believe 3 that have the rectangular clarifiers, and one other one that does have rare earth capture ability at the Richard mine in Morgantown. So these ended up being very efficient, but what we did was we brought in truckloads of AMD from the A34 site, and we processed it either through the clarifier or in these 3,000-gallon processing tanks, and made the HPC to scale up our operations before we went to the pilot facility. So as I said, we did get awarded by DOE to do the project. The A34 plant is a 500 GPM AMD treatment plant on average. We also partnered with Rockwell Automation on that project and Solmax. Rockwell Automation did all the automation and controls on our side, and as well as partnered with DEP for their automation. So we are all kind of using one whole system. And Solmax is the geosynthetic filtration development company. So the timeline of this project, so in March 2020, we began the engineering design. In November of 2020, West Virginia DEP broke ground on the facility. On the right, you can see that it's when the facility was being built. You can also see that there's a large amount of other restoration on the site by that photo. So this was also, more than just an AMD treatment plant. They removed the high wall from the site and did a lot of earth moving on this site to kind of modify it and make it better for the future, independent of our rare earth process. So this plant would have went in regardless of us to meet environmental compliance for the water discharge. In 2022, WRI mobilized to the replant for construction. West Virginia DEP started to plant and first treated water in September of 2022. And WRI started partial operation of the rare earth plant in October of 2022. Excuse me. The final plant commissioning was in March of 2023, and officially we ended this project in December of 2023. Our goals in the project was to separate the gangue metals from the feedstock, capture and dewater pre-concentrate, create high purity mixed rare earth oxides suitable for elemental separation, and a demonstration of an economically viable or feasible process. So below is a few pictures of our pilot plant. So we have the dewatering and the leaching process. We have some pictures in the middle of the solvent extraction and stripping area. And then we have the dewatered pre-concentrate on the right from the geotube bags that Eliza showed earlier. So the plant resulted in a fully automated system that is remotely monitored. That screen capture on the right is a screen that I could view right now on an iPad, or a DEP operator can as well. This can be monitored 24/7. The average inflow at the time was 500 GPM. This year we're a little down because of the drought conditions, but the average of this facility is 500 GPM. We did utilize the two-stage treatment. It continues to be utilized today. We've had flows through the plant of upwards of actually 1200 GPM and successfully utilized the process. And the first pH split has successfully rejected about 80% of the iron. The second pH split generates about almost 1/4 gram per liter of HPC. And thinking about that, coming back to Eliza's point earlier, that this is a really kind of an operation to pay for your operational costs for recovery, you don't get a lot of material out of AMD. So the tree grade of that material, or the total rare earth element grade, is about 0.6%. So only 1%, a 0.5% really of that 0.22 grams, or that comes out of a liter of AMD, is rare earth. So it's a very small amount still. We can recover about 92% of the total rare earth element from the HPC created during acid mine drainage treatment. So we have an optimal plant operation, which assumes 4-day per week operation, 20 hours per day. Due to kind of really the price increases during COVID, the rare earth side of the plant is not fully automated. So if it was fully automated and running at the efficiency, it was designed for with no downtime, full capacity of 2 PLS trains, and this doesn't account for an LREO and HREO separation. We would make about 1.7 tons of rare earth oxides a year, or 4.7 kilograms of MREO per day. We did take this a step further in the project, and we do separate to a light and a heavy rare earth oxide mixture that is our products. So out of the pilot plant, this is what we call our light rare earth oxide. It has a lot of NdPr, neodymium praseodymium, and that is really the elements of value in that mixture, commonly used in the magnet making world. You also see some other rare earths distributed in there, and we do still have a little bit of contamination in there that would be taken out downstream, but primarily calcium and a little bit of aluminum and manganese. Our heavy rare earth oxide product is primarily yttrium. This is very unique to the industry. So heavy rare earth products that are usually in the industry does not contain this much yttrium. So that makes our feedstock a little bit unique for separation downstream. And we also have a good bit of that dysprosium and terbium that we talked about earlier. This is a 95% pure product, and we do have a little bit of contaminants of aluminum, calcium, and the lithium actually would be considered a potential recoverable product. A big part of this was also the passive dewatering. The passive dewatering, basically what we're doing is capturing this HPC because the plant doesn't have full capacity, and you would not want to put a rare earth plant at every single AMD treatment plant. So we'll see later where it's kind of a design to have centralized process facilities that go to one single downstream elemental separation facility. So in this project, we worked with Solmax to develop a geosynthetic fabric out of these geotubes. Geotubes are common to the AMD treatment industry, as well as a lot of other industries for dewatering. The unique thing about the HPC is it is a very small flock, so it's very hard to capture in the geosynthetic, which led to Tenkati developing this new geotube for us. This process is now automated, so we can run this 24/7. Excuse me. And we have an average feed of 0.7 dry tons per day of HPC going to the bags. I will note that right now we do not run this in the winter, but we do have plans to modify to run in the winter. Hopefully this year, possibly next year. But we do run typically from March to this year. We actually ran all the way till November. This picture is a little outdated, but we're actually on our 4th geotube now being deployed and are up near 100 tons of dewatered HPC. The slurry going into those bags is about 1% solids on average. So it's a very low solids content slurry that then dewaters to a target of 40% solids in about a year. So if we were to capture every single bit of HPC that was generated and had a 600 GPM average flow, we would capture about 729 dry kilograms of HPC per day, or 266 dry tons per year. This would be 9.7 kilograms of mixed rare earth oxides a day at 90% purity, and assuming an 80% recovery of total rare earths through the whole process, which would give us a grand total of 3.6 tons of MREO per year. Additionally, we would be looking at 7.2 tons of nickel and cobalt, 36 tons of manganese, and 17 tons of zinc per year, which are all critical on the critical minerals list provided by the United States. So we would have a grand total of 63.8 tons per year of rare earth and critical mineral oxides that could be products produced from this single site. In 2024, we continued operations through other projects at the plant. We designed and implemented an automation system that fully automated the HPC transfer and dewatering. This is really critically important because due to the changing flow, you do not have a consistent amount of HPC that is generated each day. So to limit operator influence, we wanted to be able to account for those changes to always run material either to the rare facility or the dewatering area. We also implemented a new polymer system that aids in dewatering. So while I did present that 0.1 to 0.2% dewatering rate earlier, it is looking like it might be higher than that, but we won't have results on that till likely this spring with the new system. One thing we did not get to do on the previous project that put in this plant was really look at the filtration within the process. So we have now implemented a rotary drum filter. These are commonly seen in coal preparation plants, but we use this to filter out intermediate residuals and products during our process to make it more efficient. In 2023, we were awarded a project by the Department of Defense to expand our operations to a hard rock facility. This took place at the Horseshoe Bend Water Treatment Plant in Butte, Montana, at the Berkeley Pit. The Berkeley Pit is a very famous site because it's a very extremely large pit of acid rock or acid mine drainage. Currently is a blue color, and you can kind of overlooks the whole town. In this project, we partnered with Montana Resources and Montana Bureau of Mines and Geology to work out there with us and successfully complete this project. And we deployed our developed technologies to generate and capture the HPC and generate LRU and HRU products. So this is a real test of seeing how robust our process was across multiple different sources.
Hey, Dave. Hey, I just want to be cognizant of time. So we've got time for our third presentation. I know you're almost done with your slides.
Absolutely. So looking at the results of that facility. So this is the Horseshoe Bend plant on the left, and those are the geotubes deployed there on the right. We had very similar results, actually better dewatering because of the change in material, which started to kind of emphasize the need to evaluate feedstocks as we bring them in and integrate them within the process. So the project resulted in a 30-ton per year of rare earth elements that could be generated from the plant, but more critically, they can produce 7,500 tons per year of critical materials, mainly zinc, which would really help the economics at this facility. We had a successful generation of that HPC. It did have a lower rare earth grade, but a much higher critical mineral grade. And we also successfully used the WVRI process to generate those high purity light rare earth and heavy rare earth oxides. We did design in this one a zinc capture process. It is still being designed in conjunction with Montana Resources, but this is really, the zinc was the issue of getting high purity rare earth oxides out of this, so it kind of emphasizes the need to evaluate different sites before implementing this. Lastly, we did have a central refinery development project. It's still currently going on. So Virginia Tech and L3 Engineering partnered to develop and design first of its kind US-based rare earth element separation facility using AMD sources. It utilizes the concept of a regional midstream HPC to MREO processing plant to a single downstream elemental separation facility. And currently, we're in the process of validating some of those design parameters and finishing a business case required by DOE for the project. And as you can see, so the idea is to take similar acid mine drainage feedstocks and then generate an MREO or LREO and HREO product from a few facilities and then take them to hopefully West Virginia for a central refinery to separated rare earth element products. We did have, I forgot about this one, but we did have another project awarded that just started October 1st of 2024 that will allow funds to both operate the rare earth facility at A34, but also funds the development of unconventional separation. So I talk about these extractants. A lot of the extractants are sourced from China. We are working on both what are called ionic liquids, which will be kind of a more environmentally benign and efficient extractant compared to those of a solvent, which is like a kerosene base. We're actually currently, where we're at on this project is we are switching to a new extractant that we have sourced from Canada, so an allied country instead of China. And that's kind of where we're majorly at right now in the development of this process. I'm kind of, to give time to Nate, I'll go through this, but really what we're trying to continue to do is find sources of rare earth elements and critical minerals and waste feeds. This is not limited to AMD. This could be any manufacturing process that we might be able to look at using extraction processes. We want to scale up the AMD treatment to restore watersheds while recovering rare earth elements and critical minerals. And one of our large things is encourage and support government policy for the treatment operator to get the rare earth element ownership, like in West Virginia, throughout the U.S. And we're also seeking the protection of rare earth element pricing in the United States because China, currently owning the market, has the ability to crash the market price, which would make it not economical in any way we did this to capture rare earth. So we're really looking for some government support. And that is all I have. I thank you guys for listening to the presentation and look forward to any questions later on.
So I'll go ahead and get straight into my presentation. I know we're short on time, so if anybody has an out at 11 and needs to leave, you won't offend me, but if anybody wants to stick around and hear, I'll try to go through as quickly as I can. So I'm Nate DePriest. I'm the engineering manager here at WRI, and we'll be shifting gears a little bit. I'll talk about what we're doing here in terms of watershed scale restoration of AMD, and I'll touch a little bit of how that ties into our REE-CM programs. First, some basics on watershed scale restoration. We look at it as an alternative to point source treatment. So conventionally, AMD sources are treated individual sources with individual systems. The watershed scale approach takes a centralized approach to AMD treatment by consolidating those sources into one location with the goal of maximizing restoration while minimizing treatment costs. So the schematic you can see is just a representative of what we see in a lot of watersheds here in Appalachia. You have mines discharging AMD to multiple tributaries, which under normal operating conditions are either impacting those streams or treated individually. In the watershed scale approach, we intercept those in some way and convey them to a centralized treatment plant where we discharge treated water. So we don't just restore the stream downstream of the treatment system, we also can potentially restore those tributaries upstream by eliminating the sources. This approach does require that we identify and quantify all the sources in the watershed and further restrict them. Because it's an alternative to the existing regulatory approach of point source treatment, you do need to document the cost benefit and prove that you'll be able to meet whatever your restoration target is, and that's on a watershed scale. So something like TMDL or designated use. The main challenge is that it is outside of the existing permitting structure. Jurisdictional concerns on the DEP side of whether it's a pre-law AML discharge or a post-law special rec discharge or even an active discharge that's currently being treated. And that also impacts the finances. So particularly on the DEP side, whether we're treating AML or special rec discharges determine what pots of money our treatment costs can come from. There is higher initial capital costs because we're building a larger system. But because we're accounting for all sources, we're able to restore more stream miles at a lower long-term treatment cost. And like Dave and Eliza touched on, there's potential revenue benefit from rare earth recovery. One watershed example of this approach in West Virginia is the Muddy Creek watershed. So it's responsible for about half of the acid loads of the Cheat River. Before centralized treatment, there were multiple individual special rec treatment systems for the regulated discharges, but the unregulated discharges were not accounted for with treatment in any way. And that was the vast majority of pollutant load in the watershed. So yeah, DEP spending a lot of money on treatment without meeting their restoration goal. The alternative on the watershed approach, they designed and constructed the TNT treatment plant, which consolidates AMD from multiple deep mines throughout the watershed. On the regulatory side, that did require them to get a in-stream variance from the DEP because they were replacing individual permitted discharges with one centralized compliance point. But since it's been operation, they have seen lower long-term treatment costs and improved restoration in the watershed. What WRI is doing specifically in this realm, we do have a active project with DEP abandoned mine lands that's funded through the bipartisan infrastructure law that we're entering currently in our second year on. The objective is to evaluate watersheds throughout West Virginia and prioritize them for implementation of this approach to DEP. So we characterize the watersheds, we prioritize them, we develop conceptual designs, and through all this, we collaborate with a bunch of state and federal agencies and local nonprofit groups. And because it's BIL funded, one key distinction is that it's focused on abandoned mine lands. General approach to the project, we start with the characterization, so identifying sources, sampling them, and quantifying both pollutant loads and rare earth loads if we're interested. We can use that to perform a preliminary project prioritization. So that can be based off what the pollutant load is, what jurisdiction the sources are. And from that, we identify watersheds that we want to complete conceptual designs for. That's where we actually set what's the load reduction goal, evaluating different treatment alternatives, what are their feasibility and costs, and is there any potential rare earth revenue. That feeds back into project prioritization. Where those factors get included in our prioritization. Ultimately, we're trying to get to a project that we can hand to DEP that they could implement through a design bid build process. On the characterization side, first starting with identification, we can do that in the desktop or in the field. This requires a lot of coordination with state and local agencies and watershed groups, community, identifying what jurisdiction sources are. From that, we can move into sampling. We'll go into watershed, identify some primary sources we'd like to sample. Based off the results from that, we can decide if we want to do a broader sampling through the watershed and then establish routine monthly sampling if we want to have a characterization for conceptual design. All that leads to our characterization where we define all of our pollutant loads and what our load reduction goal would need to be in treatment. Results so far, several hundred samples collected to date, at least 14 watersheds and several treatment systems in West Virginia and Maryland. From all the sampling we've done so far, we have about 9 watersheds on deck for further characterization. Right now, we're actively looking at 4 of those watersheds, and you can see results on acid load on the left, rare earth load on the right for each of those watersheds based off the jurisdiction of the AMD sources, which we always have to worry about. On the existing system side, this is more focused on the rare earth recovery side. So as Dave and Eliza mentioned, rare earth recovery is rooted in conventional AMD treatment. So the easiest way to recover rare earths is if you already have the treatment infrastructure to do so, or you could easily retrofit your treatment system to do so. So we looked at several systems. Just a couple things I wanted to highlight here is just because the system has a high concentration, like you see on the left, doesn't necessarily mean it has a high load. So we're always beating the drum of getting good flow data, and that's really important when quantifying loads in a watershed. Also, you always have to worry about jurisdiction. Even if you have a high rare earth load like you do with the TNT plant, which I talked about already, you start to get into jurisdictional complexities when you're mixing treatment of pre-law and post-law sources. This is just another representation of the jurisdictional concerns. So you can have a watershed that's almost entirely AML. You could have one that has significant contributions from either post-law special rec or post-law active discharges. And that has to be weighed against the potential restoration benefit of those watersheds, which you can see for each of our priority watersheds in terms of how many stream miles are impaired. So how many stream miles could we potentially restore? On the prioritization side, this is currently in development. The goal here is to get a tool that we can objectively as possible rank watersheds for implementation of the approach. So starting from the left, you have your broadest categories, then subcategories, then individual criteria. Those individual criteria are what you use to grade a watershed and determine, compare it from watershed to watershed, where should we allocate our resources if we're going to implement a watershed scale restoration project. Then in the conceptual design area, for all those priority watersheds I mentioned, we are working on conceptual designs that will ultimately give to DEP for them to decide if or how they want to implement them. On our side, the strategy is we continue our monthly sampling, which gives us our good characterization. We can do additional investigations like piezometers if we're interested in the mine pools themselves. When it comes to managing the water, you can do a lot of things. If you have small discharges that are hard to treat, you could do something like grouting the entrance that AMD discharges from. That can just eliminate that discharge and have it pop out somewhere else that it's easier to treat at. You can use the mine pools themselves as conveyance. So if you have a source in a location that can't be treated, you can put it back into the mine pool to be conveyed somewhere else to be treated more efficiently. Ultimately, we're trying to capture as limited number of primary sources as we can and convey them to a treatment plant with as limited conveyance infrastructure as possible. This is just a example watershed of one of our priority watersheds. This is Greens Run in the cheat. The transparent layers are extensive underground mines, and the triangles are AMD discharges that we've identified and do routine sampling on. So this just gives you an idea of the scale of the type of impacted area you're trying to manage and how many individual discharges you would either have to treat individually or consolidate in some way with this approach in order to effectively restore the impacted streams. One final thing I wanted to talk about, this is a separate project that we have through the Department of Energy Core CM program, but it's relevant to our efforts with DEP. So the MAP Core project, and it's focused purely on characterizing the rare earth occurrence in AMD throughout West Virginia. So we are focused on coal AMD discharges in West Virginia, but we've looked at other AMD types like hard rock, other areas of the country, both close like Pennsylvania and far away like Montana. Looked at both regulated and unregulated discharges with and without treatment. In the context of our DEP project, this is very valuable because it supports our preliminary sampling. Anytime we go to a new site, we can use this project to sample it and make that first decision on whether or not we want to sample more in that watershed. So far, we've sampled over 400 unique AMD sites. We do have a next phase of this project that's currently under review from DOE. And if accepted, that'll expand our effort to the Appalachian region as a whole.